Do stars go through a midlife crisis? Actually, no, because just like most people, non-celebrities anyway, middle age for a star is a fairly stable part of their life. And that's because of this delicate balance between the outward push of pressure and the inward pull of gravity. So the center of a star is really warm, it's really hot, and because it's hot, those particles are jiggling around and there's that outward push. But because stars are also really massive, they tend to gravitationally contract as well. So while a star is on the main sequence, that outward radiation pressure and the inward gravitational pull are balanced with each other. And we can look at that by thinking of the core having some sort of built-in thermostat. So let's say there's a drop in the core temperature. When there's a drop in the core temperature, that means there's less fusion going on, so fewer particles fusing together to make heavier particles. That causes a decrease in pressure. So notice this orange pressure arrow smaller, which means that there's a greater gravitational pull, which means the core collapses, and the core collapsing pushes the hydrogen particles together more, which increases the fusion rate. So if there's a drop in temperature, that causes a drop in fusion temporarily, which causes a drop in pressure, which means that the core contracts, which then increases the fusion rate. Let's say the core temperature increases. That means that more particles are fusing together to create heavier particles. Well, when more particles are doing that, then the pressure increases because there's the increased temperature. Outward pressure increases, which expands the core. Because the core is now larger, these particles are on average farther apart and then don't fuse as much. So that brings the temperature back down again. So both sides of the cycle have a built-in process here to regulate the temperature, and that's what happens while the star is on the main sequence. So here's a main sequence star, also known as a tasty jawbreaker. We've got the core here, burning hydrogen, converting it into helium, and then we've got the outer layer, the photosphere, and then the radiation layer here. As the star expands, so as the temperature of the core gets hotter and hotter, that means more and more hydrogen is being converted into helium. That's increasing the temperature, which is sort of like turning up the flame on a hot air balloon that expands the balloon outward. So an increasing star size, converting from a main sequence star to a red giant to a red supergiant, is like turning up the flame on a hot air balloon. And the turning up the flame is really this fusion here. So a couple slides ago, I showed you this. This is a more complicated version of it. If you want to pause this and look at it with more detail, that's certainly fine. But basically the net result is 4 protons, so 4 hydrogen nuclei, fusing together, producing some extra products such as positively charged electrons called positrons, some neutrinos, some radiation, and the end result is a helium nucleus. The mass of the helium nucleus is less than the mass of the things that went into it, these 4 protons, and that slight difference in mass is converted into energy, and that's what fuels the sun. So it's the conversion of hydrogen nuclei or protons into helium that causes the energy. Each of those conversions is just a teeny tiny bit of energy, but the billions and billions of those conversions happening, means lots and lots of energy. This is an HR diagram which shows the evolution of the sun. So the sun, I'm going to talk about the sun moving on this graph. The sun itself is not moving. What's happening is as the sun ages, its temperature changes. So that means it shifts along the x-axis, and its luminosity changes, which means the y-axis variable switches as well. So each of these points on the graph represent an ordered pair of temperature, surface temperature, and luminosity. So as the sun ages off of the main sequence, That's hydrogen being converted into helium. And that happens, the sun grows in size, meaning it gets more luminous, and cools off. The center is hotter, but the surface is cooler. And remember, this represents the surface temperature. That's what we can see. Well, when the core gets hot enough, then helium can start to fuse. Because helium nuclei are two positive particles, two protons, it's even tougher to get two helium nuclei to stick together. So you need a really high temperature for that. Once that happens, the star shrinks a little bit, so it gets less luminous and it heats up. But then pretty soon that ends and you end up with a carbon core, an inert carbon core. And as the outer layer starts moving out and moving out, it turns into what's called a planetary nebula, and I'll show you some pictures of those. And then what's left behind, and a few tens of thousands of years, the planetary nebula spreads out and it's so diffuse, it's just basically background cloud material. And what's left in the center is a white dwarf, an object that's about the mass of the sun and about the volume of the Earth. So some possible sun endpoints. These are both examples of planetary nebula. The Helix Nebula, this is spherical. We're seeing it edge on, so it looks circular, but someone who is looking at it from this point of view would also see it roughly spherical with the center sort of clear like that. And this little dot in the middle is the white dwarf. Another possibility, some planetary nebulas, depending on the star's orbital rate and some other parameters, get this sort of an hourglass look, or in this case a butterfly look. And we can't see the white dwarf in this one, but at the center of this sort of symmetric, nice pretty shape is a white dwarf. Tasty jawbreaker. Actually, no, the core of a more massive star. So this is a star that is maybe 10 times or greater the mass of the sun. And because it's so much greater, there's more material there to burn. So more quickly, the hydrogen is burnt and creates a helium layer. And more quickly, the helium layer becomes hot enough you can push those helium nuclei together to form even heavier molecules. Then you can push those heavier, so carbon, then you can push those molecules together to create heavier, and that ends up at iron being in the center. And iron in the center, that when the time comes for those two things to be pushed together, energy is no longer released. So at each of these tasty layers of the jawbreaker, converting from the lighter particles to the more massive particles, the less massive particles to the more massive particles, that releases a little bit of energy. So hydrogen to helium releases a little bit of energy. Helium to carbon releases a little bit of energy. But the fusion to iron, beyond that, that does not release any more energy. And remember, it's that energy, there's that interplay between the pressure and the gravity. So when two things fuse together and that produces energy, that means there's outward pressure to balance the inward gravitational pull. When two particles stick together and that no longer produces energy, that means that outward radiation pressure goes away and the inward gravity dominates. Again, here's a pretty complex version of that. So the helium forming more massive items ending with iron. So why does the fusion process stop at iron? And I actually mentioned that. This sort of complicated looking graph, the mass per nuclear particle and the atomic mass. So for the first part here, when things fuse together, energy is released. And when you get to iron, then the graph starts to go back uphill again, and fusion no longer releases energy. Another view of the HR diagram. Here's the sun, and remember the path of the sun on this graph. It's not the actual motion of the sun, but the path of the sun on this graph was to grow to about this region, so cool down and get more luminous, and then it heated up a little bit when the helium started fusing and got less luminous, and then it expanded again, not reaching this region up here, and then the planetary nebula phase, so the outer layers just started poofing off, and what was left was a white dwarf, which ends up down here. More massive stars, they evolve much more quickly, and they go right to the supergiant stage. And if you remember HR diagrams from a previous video or from your textbook, up here, these are the supergiants, so the red supergiants such as Betelgeuse or Antares. These don't actually end up, though, as white dwarfs. These end up as supernova explosions, so they don't end up as planetary nebula and then white dwarfs. They end up as supernova explosions. An explosion, that's perhaps a slight loose use of the term. And then they end up as either a black hole, which a lot of you have heard of, or a neutron star. Neutron star is the more common endpoint because the less massive supernovas become neutron stars, but the more massive supernovas do become black holes. And one well-known remnant here of a black hole, this was a star that went supernova about 1,000 years ago, and this is the result here, the Crab Nebula supernova remnant in the constellation Taurus, which is viewable. If you're at a super dark site and you have really good binoculars, you can see it with binoculars, but certainly with a small telescope. So don't watch any more videos, go out and look at the night sky.